time, so we consider it what we call a short exact sequence of chain complexes, A, B, and C. So we had the following community diagram, where the columns were short exact sequences, and the boundary homomorphism acting in the horizontal direction. And so we started to prove a theorem that the homologies associated to these three different chain complexes are related via the following long exact sequence. This is a map induced by I, and then there will be a map induced by J, and then there will be a map which we defined before, and then we will by D, and then we will repeat, but N changed to N minus 1. So the theorem that this is a long exact. And so we proved exactness in this part. So we proved that the image of I star is the same as the kernel of J star. We also proved exactness here, and what is left is to prove exactness in this step. So we want this was the third part. So we want to show that the image of D here is the same as the kernel of I star. So this is what was left to show. And again, we can split it into two parts. The first part will be to show the inclusion in this direction. So let me take some element in the image. So it will be D acting on some element in homology of complex C. So here gamma is Cn, and it represents a class in Hn of C. This means that the boundary map should give 0 acting on gamma. So this should be a cycle. So we want to show that this is also in the kernel of I star. So if we act I star on this element, this should vanish. So let's check this. So by definition, so here we want to use the definition of the map D here. So this will be I star, and here I use the definition will be some element in homology of complex A represented by alpha, where alpha is related to gamma by the following system of operations. So it's gamma is related to some beta by map J, and then the beta should be equal to I alpha. Okay. So by definition of the induced map, this is the same as the class of I acting on alpha, and then we use the definition, so we can replace I alpha with D beta but since this is d of something, this is 0. This represents a trivial element in homology. So indeed we started with some element here and showed this is in the kernel of the star. Now we want to show the opposite inclusion, that image of D contains kernel of I star. So let me start with some element here. So alpha will be element of AN, and this will be element HN of A itself. So again, since this is some representative of element in homology, its d of it should be 0. So, and also we want, since this is in the kernel of I star, so I star of alpha, which is by definition is class of I alpha, should be 0. But this means, so since I of alpha represents a trivial element in homology, this means that there exists some eta such that this is equal to d of eta. Right? So this should be a bound for some eta in Bn plus 1. And so let me remind the definition. So if I again use the definition of D, this should be. So I can say I can use. I can imagine that this eta plays a role of beta here. So using this definition of D, if the class g of eta so d of g of eta should be equal to the class of alpha, right? And this will be my gamma in the definition, and eta will be beta in the definition. But we have to check, one thing we have to check is that this is a valid element, a valid representative of the element in homology. We want to check that d of it is 0. And this is indeed the true because dj of eta is the same as, so we can exchange d and j, so it will be j of d of eta, which is j using this equality, this is j of I alpha, and this is 0 because we know the composition of I and j is stereo. So we checked this inclusion. And thus we checked, we proved the whole theorem. Questions? So in particular, so in the condition of the theorem, we had some arbitrary, some abstract chain complexes A, B, and C, but now we can replace them by chain complexes associated to some topological space. So in particular, so we take AM to be Cm of A, where A is some topological subspace of X. Then we take Bm to be Cm of X, and Cm to be Cm X comma A, which is by definition is a quotient of Cm of X divided by Cm of A, because this is converted to the subgroup of this abelian group Cn of X. we have a short exact sequence where the first map is given by inclusion and the second map J is given by quotient. And from the theorem above, we arrive at the fact that so you have a long exact sequence of homologies associated with these complexes, so we'll have a short exact sequence of the following form. Statement that this sequence is exact. In particular, this will allow so the fact that the sequence is exact is very constrained. In particular, if often if you know the homologies of A, homologies of X, this allows to determine homologies of the relative homologies. So let me give you an example. So let A be just some subspace containing a single point in X. So first let us see how this sequence looks when n is greater than 1. So it looks like this. So we have a Hn. So this is a this is homomorphic to just a topological space consisting of a single point. Have short exact sequence which looks like this, but we already calculated the homology of a point, so we know this is trivial for n equals n greater than 1, and this is also trivial, and so therefore this map should be trivial, and this map also should be trivial. It's a map to a trivial abelian group. You see this map is trivial. From exactness it follows that this map is injective, right? Because its kernel is image of the trivial map, so it's the kernel is trivial, so this map should be injective. But from another point of view, this map should be, if you look here, this map should be surjective, because its image should be the kernel of a trivial map. So its image should be the whole space. So this means that this should be isomorphism, right? And therefore, now let me consider, so the other part, I mean the case when, what happens when n equals, let's say 1. So we write this kind of part of the log exact sequence, so it will look like this, h1. And then it stops, right? There is nothing after 0 here, in this case. So again, this is still 0 for 1, but this is, you know, this is isomorphic to Z. And now, what we know, it's so this map is induced by inclusion. So we know that so this map is generated by a single. So this H0, the homology group here, is generated by a single singular simplexer. There only one map from a point to X0, and we know this is gives a non-trivial. This has non-trivial image here. So the generator of this group, the image of this generator gives a non-trivial generator here. So we know that this is, we already calculated that this is equal to direct sum of Z's generated over connected components, or past connected components. And so this generator just generator here maps to a generator of 1 with a Z, which corresponds to a past connected component which contains this X0. So this means that this map, we know that this map is injective, and therefore this map should still be trivial map, so this still should be isomorphic by the same reason as above. But here we have the bottom row now is considered as a short exact sequence, and as we have for any short exact sequence, the middle term of the short exact sequence can be understood as the last term of the short exact sequence can be understood as a quotient of this guy over this guy. Because this is exactly equal to the kernel of this map. And so for higher M, this is the same. So we obtain the following results of expressing the homology related with respect to a point to the homology of the original space. Questions? So here we have a homology, the relative homology associated to a space, topological space, and a subspace. So there are natural. So consider a pair of like two such pairs. So let A be subspace in X, and B will be a subspace in Y. Then we can denote map F from a pair X and A to a pair Y and B, a map. So we can write the following: this F is a map between pairs if we have a map F from X to Y, such that the image of subspace A is contained in the image in B. So we know that such map, just between X and Y, it induces the maps between the corresponding chain complexes. which satisfies this condition that it commutes with the boundary homomorphism. And so this abelian group contains Cn of A, and this abelian group contains Cn of B, as before. And if you consider the restriction, the image of this map at sharp of this abelian subgroup, this will be inside, also inside of Cn of B. This is because A is the image of A is inside B, and again, remind you that this abelian group is generated by all maps from n-dimensional simplices to which so the image in A. But if you, of course, if you compose it with F, the image will be inside B. So we follow this condition. So we can restrict. This means we can restrict F on these subgroups, and we can also consider induced map on the quotient, which we will denote by the same symbol, F sharp. So since this is by definition is the quotient of Cn of x divided by Cn of A, this is by definition the quotient of Cn of y divided by Cn of B. So if I have a map between the original spaces x, Cn of x and Cn of y, which satisfies this condition, this gives a well-defined maps on the quotients. Because if I consider here elements, model elements from this subgroup, I will get a well-defined element of this quotient. And since I have this condition for the original, for the map between the original abelian groups, I will have the same condition will hold for the quotients. And therefore, we know that for any map between some chain complexes, some abstract chain complexes which satisfies this condition, it induces a well-defined map on the homologies. Just before we denoted with F star. Again, it's defined if I take a class here represented by some element alpha, I map it to the class of F sharp epsilon alpha. Questions? Now consider, like as previously just for topological spaces, consider a pair of maps which are understood as the maps in the sense above, as a map between pair x and a to a pair y and b, where a is the subspace of x and b subspace of y. So then we can define that F is homotopic to G as maps between pairs. If and only if there exists a homotopy F X, as usual, the homotopy is mapped from X times interval to Y, such that F restricted to 0 is the same as F, and F restricted to 1 is the same as G. But now we want, so this will be just homotopy between maps from X to Ly. But we want to add a special condition so that for any value t in the interval 0, 1, we also have this condition that the image of A is contained in B. So for any t, we have a map, we have a well-defined map between pairs. So then using such notion of homotopy between map between pairs, where a pair is a logical space and a subspace, we can show the following proposition. F is homotopic to G, again as maps between pairs. Then the corresponding reduced maps are equal. So they're equal as the maps from Hn from relative homology of X with respect to A to relative homology of Y with respect to how do we prove this? So let me. So we already showed this proposition when just for the usual homology, for non-related homology, where F and G were two homotopic maps between Hn of X and Hn of Y, right? So we already showed this proof this theorem. And in the proof of the theorem, we had a certain prism operator defined, right? So consider the prism operator previously. So I can do this because, in particular, so the maps between pairs I can in particular consider as a map, just a map from X and Y if I forget about M. And they will be homotopic also as just ordinary maps. So this was a prism operator. It was operator P acting on Cn of X and valued in Cn plus 1 of Y. And again, it's easy to see. So if we take a subspace of Cn of X, which is Cn of A, so I consider a singular simplices which mapped inside A, the image of the subspace under the action of the prism map will be inside Cn plus 1. This will follow from the condition that F satisfies this property. Because the prism map uses essentially composition of F with a simplex map, with a singular simplex map. So if F satisfies this condition, we immediately get this. The resultant simplex will be contained inside B. And again, so since we have a map satisfying this condition, it induces well-defined map on the quotients. which is by definition this relative chains. And so before, the important property of this prism map was that dp plus pd was equal to G sharp minus F sharp. This property was satisfied for map for the original map P. It will be satisfied. It will be also satisfied for the map between quotients. This still holds. On quotients. So this can be considered. This equality can be considered as a equality of homomorphisms between homomorphisms from Cn of xa to Cn y comma b. And again, so before we showed that for any, if a pair of chain maps between some two abstract chain complexes satisfies this, the difference has the following form for some operator P. Then the corresponding induced map on the homologies will be just the same. So we call this property that this is P is a chain homotopy. P was a chain homotopy. This is just reminding what I had before. And one can say that F and G sharp are chain, as a chain maps are chain homotopy. This concludes the proof that the induced maps are the same. Questions? So now there will be we start. So first formulating and then proving a very important theorem. Which is called excision theorem. And it has two equivalent formulations. Two equivalent versions. So the formulation 1 is the following. So let Z be a subspace in A, which is a subspace in X, such that there is additional condition that the closure of Z, to remind the closure can be understood as Z together with which includes its boundary. Includes the add all boundary point with the not already there. So the closure of Z is inside A, and then the so we can consider inclusion map as a map between pairs X minus Z, where we understand this minus is a set minus. So this is a complement of Z inside X. And this will be, so since A was subspace in X, this complement will be subspace in this complement. And this is included in, of course, this is included in X A. It seems the restriction of inclusion of this guy on this subspace will be inclusion into A. So in a sense, this inclusion as a particular case of general map between pairs, whereas this is a subspace of this guy, this is a subspace of this guy, and it induces, as we showed above, such map between pairs induces a map between corresponding homologies. And the non-trivial fact that this induced map will be isomorphism. Okay, this is I, this is I star. And this is isomorphism. As the integral statement, this is isomorphism. So this is the first formulation. The second formulation, which will be equivalent to this, as we will see in a moment, is that let A and B will be two subspaces of X, such that interior of A united with the interior of B. Again, I remind you, interior is by definition A minus the boundary, so we exclude boundary. So interior of A and interior of B covers completely X. Then the statement that inclusion of B, comma intersection of A and B, which is this is the subspace of this guy, and we can include this pair into X and A. And such an inclusion also induces isomorphism between the corresponding homologies, relative homologies. So we'll prove this a bit later, so we'll need a certain lemma to prove this first. And we essentially will start proving this, but we will first prove some auxiliary statements. But first, let us show, it's easy to let us show that these two formulations are indeed equivalent. So in the version 1, we have, so what we had? We had some logical space X, then it had a subspace A, and inside A there was a subspace Z. So Z, the closure of Z was inside A. Now, so we want to relate this setup to the setup in version 2. And this is done by just identifying B, the subspace appeared in version 2, with X minus Z. Or equivalently, if you want to express this equation Z using B, if you want to go from version 2 to version 1, we say that Z is X minus B. So how does it look? So if B is X minus Z, so B is systematically this subspace. And then it's easy to see that if you take intersection of A and B, this will be the same as A minus Z. So it's easy to see from the schematic picture. the intersection will be this exactly A minus Z. So indeed, if we compare two formulations, this will be the A intersection of B is exactly the same as A minus that, which is what we use. So we just have identity between this guy and this guy, and identity between this guy and this guy. But we also need to, so there are some additional assumptions. We need to see that the assumptions are also equivalent. If you make this correspondence between B and Z. So there was assumption, so in version 1 there was assumption that Z, the closure of Z is inside of A. So if we use the fact that so B is equal to X set minus Z, so this means if we or in other words, Z is the complement of B inside X. So this means that if you take a complement of interior of B, this would be a closure of Z. So here, if we remove all boundary points, this means that here we should add all boundary points. And so, taking account this property, we can see that X then is the same, can be represented as the union of interior of A with interior of B. So this shows that the two formulations are equivalent. Okay. So the proof of the excision theorem will be quite long, and we will need to introduce certain notations. So let me denote by this curly U as a collections of UJs. So each UJ is a subspace in X such that we want the subspaces be such that if you take a union of all interiors of the subspaces, it will cover X. So the interiors, in other words, the interiors of this subspaces Uj, they form open cover of X. And then we can define, so using this collection of subspaces, we can define certain subgroup which will denote Cu n of X, subgroup of our usual Cn of X. So again, so this is so by definition, which you already know well, this is this abelian group contains all linear combinations with integer coefficients of singular simplexes sigma I. So each sigma I is a map from delta n to X. So how we define a subgroup? So this subgroup will contain elements also of this form, so they will be linear combinations of sigma i's, of sigma i's, where we want to require additional properties from sigma i's, so that so sigma I is again it's still a map from delta n to X, but we want the property, additional property, there exists some j such that some index j, so such that the image of the sigma I is completely inside the subspace labeled by this integer. So in other words, each guy here is a singular simplex in the sum, is a singular simplex which is completely contained in one of these UGs. And this is naturally an abelian subgroup in this abelian couple. And so we have a map on Cn of x, we have a map D, the boundary map, which acts from Cn of x to Cn minus 1 of x. And so we can consider its restriction on this subspace, subgroup. Which we will denote, so this will be a map, this can be understood as a map from CMU of x. So by definition of this boundary map, we just, so for each sigma we just take a certain restriction on a linear combination of restriction of sigma on the faces of delta n. But of course this restriction will also satisfy this condition that the image of sigma will be contained in a certain uj. So this restriction can be assumed the map from Cn u of x to Cn minus 1 u of x. And we will denote it again by just the same letter, gt. This was a map on Cn of x, and this was the homomorphism on the So this, and this, we still have, since the condition that d squares is 0 still holds. Since it was true for the original d, it will be true for, of course, it will be true for the restriction. So this defines a chain complex. Corresponding homology, which will denote HUN of x, which is a homology of this complex. So we have some homology group that's associated to X and a collection of subspaces U such that the interiors they form open cover of X. Now we want to show the following lemma. So the inclusion I from this abelian group to Cn of x. So this is defined by as a some subgroup. Is a chain homotopy equivalence. That is, they exist, what exactly this means, there exist some map rho from Cn of x to Cn u of x, such that composition of rho with I and composition of the other way are chain homotopic to identities. This means there exists inverse of I up to chain homotopy. Chain homotopy is we defined before, so there should be existence of a certain chain homotopy operator such that the difference between of this guy and identity is equal to D times this operator plus this operator times D. So the proof of this lemma is quite hard to prove. It will require some rather lengthy calculations, and actually, so I will in my proof I will skip a certain technical details. I will focus on kind of geometric part of the proof. So if you want to see details, you can see them. See the more detailed proof. See in proposition 2.1 in lectures. But this is not. This is something which will be not used anywhere later in the course, so you shouldn't worry about it. So this is just you are really interested. You can see there. Okay. So let me fix some sufficiently large integer number n. And so as in principle we already had this notation, but so now I want to understand this in a bit more general sense. So let me consider this the sequence in brackets such that each element here I want to understand as a point in Rn, Euclidean space of dimension n. So the whole thing is I can understand the subspace this guy, which is defined as follows. So it's defined as a space of points in Rn, which are linear combinations. Sorry, here the vi, which are linear combinations of points vi. So, of course, since Rn I can understand the vector space, I can do arithmetic operation. I can multiply them by numbers, and I can add them such that the sum of the coefficients is 1. So this so before when okay, let me say the following. So this can be understood questions as a linear map sigma from delta n to Rn, where, so if delta n, if I choose again, so I use the same notation for the simplex, where these guys denoted the vertices of the simplex. So suppose the vertices of this kind of the standard simplex are denoted by W's. Such that the linear map such that the value of Wi is exactly Vi. So if so if the points here, if the i's are not simultaneously contained in n-dimensional, n-1 dimensional hyperplane in Rn, sigma is invertible. So it provides, sigma provides one-to-one correspondence between so the between the standard simplex delta n and this subspace in R. So the linear map, of course, the linear map is completely determined by the values of sigma on vertices, because any other point is a linear combination of this vertex. So essentially, I can understand the point. So this kind of these guys here, I can understand as kind of if V of general position. So if they satisfy the condition, I can understand them as an n simplex embedded into Rn. And but it can happen that it's kind of it's degenerate. So it may happen that, for example, a triangle is such that the 3 points lie on the same line. So it can happen to be degenerate. And so then I can define the following, let's say, the abelian group. So we shall denote by LCN. So this will be a group which contains formal linear combinations of lambda j's, where each lambda j in the linear combination is equal to is a subspace of Rn in this form. Some elements in R. So again, I can understand this as a possibly degenerate. By degenerate, I mean the certain vertices can I mean, it can have essentially zero volume. So again, if I understand these lambdas as this again, the coefficients are before integer numbers, and so I can understand this space LCN, this abelian group, as a subgroup of our usual Cn of Rn. Because each element here, each generator here, can be understood as a linear map from delta M to Rn. Just a special map which is linear. And but I also want, so this is a definition when n is greater or equals than 0, but I also want to extend this for when n equals -1. So I just define this as a subgroup generated by kind of empty sequence. So there is no vectors, no vectors here. So now I'm interested in construction of certain operation or certain homomorphisms on these spaces. So first, so let me operations on. So the name here is because this is an LCM, because this is a linear chain. This is the arbitrary chains or arbitrary maps from delta M to Rn, but here we can just consider linear maps. And again, the linear maps are completely determined by the values, by the images of the vertices. And these images of the vertices we denote by these. So again, here we had a boundary homomorphisms, and we will again have a boundary homomorphism here, which okay. In principle, it can be assumed as just a restriction of boundary homomorphisms on this guy, which we already know how it's defined, but one can write it more explicitly. So if D acts on some arbitrary generator of this guy, so the arbitrary generator is of this form, we will have certain formula which you should be familiar with. So it will be sum of i's, and so the right-hand side will be a linear combination of this kind of sequences of elements in Rn, where we remove is vectors. So another operation, so let me consider some point in Rn. Then for each point, let me, for each such B, I can define a homomorphism which are denoted by phi B, is index B, to be homomorphism from LCM to LCM plus 1. And again, I need to define it just on a generator, on an arbitrary generator. Arbitrary generator, I will map to a sequence where I add B so let me just give you examples. So suppose n equals let's say 1. So I have some point in my Euclidean space Rn, B0, some point B1. So this is my B0, B1, and I have somewhere else some point B. So this kind of this guy is the image of this guy will be this triangle. So we start from the interval and we get it. But again, it may happen that so here we don't have a restriction that these guys they should not degenerate. So it may happen that they all lie on the same line. It will be something like this. Degenerate element. 0, 1. Okay. So this map satisfies the following important property. That first, if you take a composition of this map for some B with D, this is the same as identity map minus the composition in the opposite direction. How do we check this? So let me again take a left-hand side and act it on some arbitrary generator. So first we act by phi b, so we add, the only thing we do, we add b here. And then we use the definition of d, so this will be, so the first term we will remove b, then with minus sign we remove instead b0, then with plus sign we remove v1, and so on. And so we can separate the first term, so this will be the first term will be identity acting on this guy. And all other terms, we can see that this is the same. So we have b here in the first place, so we can write as the minus b phi b acting on d. Well, okay, let me write it more carefully. This phi b acting on d1 bm minus d0 d2 so on. And of course here we have a definition of d acting on this guy. So we have an identity acting on this guy minus phi b composition is identity acting on the same guy. So this shows that we indeed have this property. Okay. So now, another preparation which we want to do is to prove this lemma. So we want to define what is called the barycenter of some element lambda of this form. So we define it as a point B in Rn, which is just the following linear combination of vertices here. Their sum divided by n plus 1. So you can see this can be the center of mass, center of mass formula if I put unit masses in the vertices, Vr. So this is barycenter B of lambda, which is not B lambda. So for example, if lambda is just a point, B will be the same. If lambda will contain just one vertex, it will be the same vertex. If lambda is an interval, again it can be degenerate. It will happen that V0 is coincide with V1, but B will be middle of this interval, and if lambda is triangle, possibly degenerate. This B will be intersection of medians of this triangle. This is the same. And so on. And then we want to define a notion of barycentric subdivision. Of lambda. And we will define it recursively. With respect to n. So what does this mean? So if lambda. So what do you mean by barycentric subdivision? So if lambda is the vectors is v0, vn, then we want to decompose it into union of certain elements of this form. There will be b lambda, comma, the one of the vertex, so it will be a union of the elements of the same form, but the vertices will be, so the first vertex will be b lambda, and the other vertices will be, well, we'll denote them by w1, well, okay, w0, or wn-1. This has the same length, and so this union means that the interiors in the union interiors are non-intersecting. And so the other guys, so this is the barycenter of lambda, and the other guys are such that if I remove this b lambda, this will be inside barycentric subdivision of a face of lambda. So the face of lambda, again, so as we had for kind of the usual synthesis, the face of lambda is what you get when you act by derivative. So all elements here, which appear on the right hand side, are faces of lambda. So the face is what you obtain by removing one of the vertices. So let me elaborate. Let me give you. So this is quite formal. Let me give you some examples so a bit more clear what this geometrically means. So this is something rather simple. So I want to define it recursively with respect to n. So we first want to define it when n equals -1. Then let's start with let's start with z. Because I mean, if you start with -1, it won't tell us much. So this will be an empty guy. So an empty guy is just decomposed into an empty guy. But so the point is also this will be just so the subdivision will be just the same point. It will be just one element of subdivision. So the point is just the same. It's trivial. Now if n equals 1, so what happens is so So we start with some interval, and so we want, we add here, this will be a barycenter, so the middle of the interval, and then the subdivision will be, so there will be just two brackets, so there will be d lambda, comma, so this is my lambda, v lambda, comma, v0, united with v lambda, comma, v1. So it's just we divide this interval into two half intervals. This is my barycentric subdivision when n equals 1. So when n equals 2, the barycentric, so lambda is some triangle, possibly degenerate, and so we'll just draw a picture. I want to write explicitly. So we start with this triangle. So the barycenter will be here. So how do I find barycenter? So first I find the centers of each of the edges, and then I draw the lines here. And so this will be b lambda. And so since when I start using recursively this formula, the subdivision will be division in this exactly in these small triangles which I have here. This is my barycentric subdivision when n equals 2. Because again, I can sense this union, so this is a barycenter. So first, when I do recursively, I do barycentric subdivisions of each edge, and then from this barycenter of lambda itself, I do this kind of combine triangles with this barycenter and subdivisions of this interval. So it will be 6. In this case, it will be 6 elements in this subdivision. Triangles. Question? Okay, now the next step is, so you want to define another operator from LCN to LCN plus 1. And so formally it's defined like this. If we take some generator lambda, it will map to b lambda, so phi of b lambda of S of acting on d lambda. And again, we define it inductively or recursively inductively with respect to n. So this is gives, and so we first define on so for n equals -1. So there are only an empty sequence, and the result is again it's an empty sequence. So this is the definition of the base. And then, so if I know the definition, so if lambda is in LCM, d lambda is in LCM -1. So if I know the definition, if I know how to define S for LCM -1, this gives me a formula for LCM. So let me again give you, so this is not so abstract, let me write more explicitly how it goes. So suppose I have this, so suppose I want to, now I want to action on some point, just on a point, so for n equals 0. So just S acts on a point, and so we want to use the definition. This will be phi, so now we want to phi corresponding to barycenter of V0, which we know this is the barycenter of just a point is a point, and then we want to act S on a D of, so the D of V0, this will be an empty guide, right? So D of V0 is, so we remove, we extend the definition of D. We say that if there is a single vertex, when we remove, we just get a list with no vertex. And this is so this is operation of adding. So S. So first S acting on this guy is the same by the base of the induction. And then we want, so this is operation of adding vertex V0. So this we add vertex V0 to nothing, we get again vertex. We get the same thing. So on N0, S also acts as identity. Now let's just consider when N equals 1, for example. So let's take arbitrary generator, some interval. And so again, if you want to use the definition, so barycenter of this guy will be B, which will be a point in the middle of V0 and 1. So one explicitly or implicit one, if you want, you can specify it as a half sum of V0 and V2. And then want to add X, S on the boundary homomorphism acting on this guy. So boundary homomorphism, so first we remove V0, we have V1, and then with minus sign we remove V1. So 0. And then by linearity, so here, so we know that for n equals 0, S acts as identity, so it will be the same as phi B acts on V1 minus V0. So this will be the same as using the definition of this operator. So we add a point B, so B V1 minus V. And so on. So you can, if you want a home check when n equals 2, write explicitly how it acts on a triangle. But you will, so it's easy to see that it's always happens that in general the right hand side will have the following form. So S of some lambda will be the sum with plus minus signs of some lambda i's, such that lambda I is in barycentric subdivision of lambda itself. In particular, in this example, if you repeat this calculation, the result will be linear. So we start with this big triangle. The result will be some linear combination of small triangles with plus minus signs. Questions? In particular, this example, we have already saw this. This is a linear combination. So barycentric distribution is just a pair of half intervals, and this we get this interval minus this interval minus this interval. Okay. So again, as a overview, the proof is very long, so we still have to continue. And so the other operator which you want to define is we will act on LCM to LCM plus 1, and we know by T. And again, we define it inductively with respect to to n. So we start from n when n equals -1. So we define just action on, because there's a single generator, action on an empty list is true. And for general n, we use the following formula. We want to use the t of lambda is equal to phi d lambda. This is the barycenter of lambda acting on lambda minus t of d lambda. So again, if you know the definition of t for n-1, you know the definition for n, because if lambda belongs to LCn, d lambda belongs to LCn-1. So we can use this formula to recursively define t. So let me give you some examples. So t, so if lambda contains just a single point, again, the barycenter of a single point is its point itself, then we just repeat here lambda, take lambda itself, and use t, so the boundary of a single point is an empty thing, and we know that this is 0, and we know how this acts to this, so we get just a pair of equal points. So in this case, you can understand the kind of interval which collapsed to a point. As I warned, this is a normal thing in our construction. And so let me give you one more example. So if t acts on an interval, so the interval looks something like this. This is v0, v1. This will be its barycenter of d. In the middle, then I take, so I use this formula, I take lambda, and then I want to act by t on the d of this guy. So d of this guy is v1 minus v. So let me write this guy, and so t acts, we know how t acts on points, so you just pair them up with themselves. We use this result, and then this operator is just adding a point b. Okay, and so now let me quickly show the following property. So we want to show that this combination is the same as identity minus S. So this is understood. So the elements here are understood as the homomorphisms from LCM to LCM. And so again, so since we have a definition of T and S by induction, so we will show this formula by induction with respect to n. So when n equals -1, the base of induction is it's easy to see. So we have in the base we know that t when n equals -1, t is 0 by definition, and S is identity. And this is indeed satisfied. This formula when t is 0 and S is identity. And the induction step is the following. So I want, so let me consider dt here. This guy acting on some generator lambda. So by definition, it's d. So I use the definition of t, which I had before, which is phi d lambda acting on lambda minus t d lambda. And then, so So I use the property, there was a property of this map phi that if I exchange, I can exchange D with phi and earn identity operator. So this is I use the formula which I showed before. This is equal to this. And so first I act by identity on this guy. So this will be lambda minus TD lambda. And then there will be minus phi d lambda d lambda minus t lambda. And so let me just rewrite this thing. And so yes, so let me repeat this guy, and now I want to use the induction assumption. So this t inside, it acts on d lambda, so it's a map from LCn minus 1. So I can use induction assumption, and so I can use this formula for this t here inside, and this means I can write here identity minus s minus dt. Right? So replace td here with this guy. Sorry, wait. No, there is not. Yes. Okay. So, okay, let me continue this quickly. So you can see, so I leave this the rest unchanged, but let me this will be d. So lambda. So I can see that lambda minus identity action on lambda will cancel. So I'm left with s action on lambda plus d action on t lambda, and then. So I use the fact that d squared is 0, so this will be lambda minus td lambda minus phi b lambda d. So since d squared is 0, this will be 0. And then here I can see the recursive definition of S. So the definition of S, this is just the same as S of lambda. So this is what we wanted to show. Well, this is not a proof of this theorem. This is just a proof of this statement. Okay, let me stop here.